Section 1.4, one-sided limits. And continuity. We actually talked a little bit about one-sided limits a few days ago. Anybody remember when we talked about one-sided limits?
You're approaching from just one side, so if it was like a piecewise function having two opposite directions, you would use one side limit, like saying the plus side is going towards this, and the negative side is going.
Okay, yeah, and that's exactly right. And it wouldn't even have to be a piecewise function. We did this sort of thing the other day. Let's say I gave you the limit as x goes to 5 of x squared minus 25 over x minus 5. And you plug the number 5 in. No. What do you do? One option would be a table. So what you could do is you could build a table, and you could plug in numbers like 4.9, 4.99, 4.999. And those numbers would all be close to 5 but smaller than 5. And we had a symbol for that. What was the symbol that we used for getting close to 5 but less than 5? We used a little plus and minus. So whatever we got for an answer here, we would write this symbol, limit as x goes to 5, and we would put a little minus right there. That just means we're close to 5 but smaller than 5. And I'm not going to work out what that table is, but I'm quite convinced my y numbers would be getting close to 10. Yes?
Minus to the left if you're coming from the negative direction.
Minus is on the left because you're coming from the negative direction. That's exactly correct.
When you're looking at it kind of like left to right, so that means the opposite side is coming from the right.
Yes. In fact, you'll even see some textbooks, I've seen books use this symbol, limit as x goes to 5, and they'll put an L to indicate I'm coming from the left. I've seen that symbol in some books. If you prefer that symbol, use it. That's fine with me. Grace?
But if x squared minus 25, I get things from the
Yes. Absolutely. So instead of solving this problem by building a table, we could solve this one analytically. Absolutely. But then it wouldn't give me what I wanted to talk about, left and right limits. So it kind of would ruin my fun. Okay? Same idea. We could build another table, and we would plug in numbers close to 5, but a little bit bigger than 5. And then we would have a symbol for that too, right? Limit as x goes to 5 from the right of x squared minus 25 over x minus 5. Or some, again, I'll see this in some books. We'll put an R there for right. Okay? So we actually did talk about left and right limits a few days ago. We didn't use them for a whole lot. Today, we're going to use left and right limits for something important. Okay? And to answer Grace's question, yes, I could have done this. This is the limit as x goes to 5. X squared minus 25 factors as x minus 5, x plus 5. And then what happens? Those reduce. And then can I plug the number 5 in? Yeah, and I get 10. So I think in this situation, evaluating the limit analytically by factoring and reducing would have been much quicker and much easier than typing it into my calculator and building that table. So I think this is a good example of where analytic is better. All right, so the kind of functions we're going to look at today are called piecewise functions. So let's see, we might have f of x equals, how about 2x minus 1 if x is less than or equal to 0, and x squared minus 4 if x is bigger than 0. Typically, the question that you're going to be asked is, what's the limit as x goes to 0 of f of x? Any guesses? -1's a good guess. Any other good guesses? Somewhere in between -1 and -4 is a good guess.
I'd say,
Either one, -1 or -4 would be a good guess. Or neither one.
I'd say you discontinuous, and then it approaches one from one direction, one from the other.
So what's the limit?
There is no ordinary.
There is no limit. All right. So I'm going to draw a quick graph of this function. Oh, I don't need my calculator to draw it. I can draw it by hand quicker than I can on my calculator. What does the graph of 2x minus 1 look like? It's a straight line. The intercept is -1. The y-intercept is -1. So here's the point, 0, -1. But I don't want the whole line. I only want the part of the line when I'm less than 0. So I really only want that part of it. And I did put a dot there. Why did I put a dot there? Because I had the equal to back in the beginning of my formula. What's the graph of x squared minus 4 look like? It's a parabola. The y-intercept is 0, -4. But again, I don't really want the whole parabola. I only want the parabola when x is bigger than 0. So I really only want half of the parabola. So what's happening as I get close to 0? If I get close to 0, but I'm less than 0, I'm coming this way, and my y values are getting close to -1. My x is getting close to 0, my y is getting close to -1. On the other hand, if I come down the graph this way, when my x values get close to 0, my y values are getting close to -4. So what would we say the limit is? Does not exist. When we talk about limits, how many answers do we want? 1. In this case, we have 2 different answers. And so the symbols we would write the limit as x goes to 0 from the left of f of x is -1. And on the other hand, the limit as x goes to 0 from the right of f of x is -4. And so our answer to the entire problem would be does not exist. The limit itself does not exist. The left limit exists. The left limit is -1. The right limit exists. It's -4. But those answers aren't the same. If those answers were the same, then we would say the answer is whatever the common number was. Correct. All right, now here's the good news. For the most part, to answer these problems, you really don't need to draw a graph. So you're going to have something like this. G of x is. Anybody got a function they like? (3x plus 7) if x is less than, let's not use 0 again because we used 0 last time, 0 less than 4. And then give me another function. X cubed plus 5 if x is greater than or equal to 4. All right. I want you to tell me 2 things actually this time. I want you to tell me that, and I want you to tell me this. What does the first symbol mean? G parenthesis 4. Plug in x equals 4. And when x equals 4, where do I plug it in? I plug it into which rule? The top one or the bottom one or both? Only the bottom one. How come? Because that one has the x equals 4. So this symbol means plug the number 4 in, and this tells me when x equals 4, use this rule. So this is 4 cubed plus 5. How much is 4 cubed? 64 and 5 makes 69. Now I want you to tell me the limit as x goes to 4 of g of x. I agree, I don't think there is one, but why not? You got to show me some work. So what you would do in this case, this is a piecewise function. You would write limit as x goes to 4 from the left of g of x is. What's the limit as x goes to 4 from the left? You use the rule 3x plus 7, don't you? Why do you use that rule?
Because that makes one where x plus less than.
This means you're close to 4, but you're less than 4. If you're less than 4, you use this rule. So I can plug 4 in. I would write 3 times 4 plus 7, which is 19. Conversely, limit as x goes to 4 from the right of g of x is 69, because now I use this rule, x cubed plus 5. So this would be 4 cubed plus 5, which is 69. So what would you say about the limit as x goes to 4 of g of x? Once again, it does not exist. The left and the right did not come out to be the same. It doesn't exist. The only time it does exist is when the left and the right do come out to be the same. Questions on that? All right, how about, I'll make up another function here. H of x is, once again, somebody make up a function for me. X to the 5th plus 32 if x is less than 1. And, I got to be clever now, 30x plus 3 if x is bigger than 1. And I want pretty much the same thing. I want to know h at 1, h at 1, and I want to know the limit as x goes to 1 of h of x. I did not. I did that on purpose. I did not want an equal to there. So the first one, the answer is does not exist. Why not? Because neither of them, I've left my x's off, didn't I? Because neither of them has been equal to 1. So the answer for that one would be, I cannot plug the number 1 in. That does not exist. As x goes to 1. 33? Why 33? You got to check from both sides. That's correct. Limit as x goes to 1 from the left of h of x is 1 plus 32, which is 33. And the limit as x goes to the right of h of x is 30 plus 3, which is also 33. So in that case, we would say the limit is 33. Questions on that one? All right, so what's happening in a picture? How come for g of x, the limit does not exist, but for h of x, the limit does exist? What's happening in a picture? Okay, what's happening here, if you were to draw h of x, you would have something like this, I think. Let's see, this would be right here. I'm going to put a little circle there. That's the point 1, 32. I put a circle there because I don't have an equal to anywhere, do I? What does x to the 5th plus 32 look like? What's that? It's kind of S-shaped, except we're stopping at 1, aren't we? We only want to the left. So it looks kind of like this. If you were to type that into your calculator and get a decent window, it would look something like that. And how about 30x plus 3? What does that look like? That's a line. The slope is really steep. The slope is 30. So that's going to be a line. It's going to be really steep. But you can see what's happening in the picture. What's happening in the picture is this part of the graph and this part of the graph are coming together right at the same point. Where what's happening with g of x here? They're not going to the same point. On one side, you're getting 19, and on the other side, you're getting 69, so they have a big gap in between. James? Yes, it should be 1 comma 33, sorry. Thank you. 1 comma 33, yes.
Although in that graph, we never actually meet.
They never actually meet because it never happens that the point 1 comma 33 is filled in. So they're coming closer and closer and closer, but they truly never meet for this problem. What creates the limit is the fact that they're both getting really close to the same number. They could actually meet there, and that would be okay. So if I had put an equal to on here, then all I would do is fill in the dot, and it would still be okay. That they would still come together on both sides. All right, so now we need to talk briefly about something called continuous. A function is called continuous at x equals a if three things have to happen. 1, f of a is defined. 2, the limit as x approaches a of f of x is defined. And 3, those two things happen to be equal. F of a equals the limit as x goes to a of f of x. All right, so let's just go back and look at this example here for a minute, these two examples. We'll do more of these tomorrow. Is h of x continuous at 1? No, why not? It fails the very first rule. The very first rule is to be continuous at 1, I need to be able to plug the number 1 in. Can I plug the number 1 in? No. So is this continuous at 1? No. In fact, this is called discontinuous. The opposite of continuous is discontinuous. That kind of makes sense. This is called, when there's one little hole missing like that, that's called a removable discontinuity. And we'll talk more about that tomorrow. So we would say this function is not continuous at 1. In fact, it has a removable discontinuity. How about g? Is g continuous at 4? Can I take the number 4 and plug it in? Yes, I get an answer. Does the limit as x goes to 4 of g of x exist? No. So is this continuous at 4? No.
So it says pass all.
It has to pass all 3 rules. Yep, passing 2 is not good enough. Got to pass all 3. This one has a name. If you were to draw this one, you would see that the two things don't match up. From one side you're getting one value, one side you're getting another value. There's a big jump in the graph in the middle. So what do you think we call it when there's a big jump in the graph? A jump discontinuity. So this one, this graph, this function would be said to have a jump discontinuity. All right. So tomorrow we'll take a quiz. We're going to have a quiz tomorrow on section 1.3, and then we will start off back here. Questions? Yes. So tomorrow we will start right there, and we'll do some more examples, Grace.
So you said removable discontinuity? What is the removable?
Well, removable discontinuity is where there's one little point missing, and we'll look at more examples tomorrow. And a jump discontinuity is where the two pieces don't come together at all.
Let's say that is something called point.
It's also sometimes called point discontinuity. Yes. James, is that your question too?
Yep,
All right.
that's my question.